what I want to do is show you that if you use dimensional analysis, you can easily conquer the mole. Okay. So we're talking about the mole, and a mole is not a fuzzy creature, okay, or a rat in a agency or something. It's actually a way of expressing very, very large numbers. And you guys are going to do this in your lab. You've got to do the activity that deals with the mole. Part of your next activity deals in small part using the mole calculation. And you have a whole experiment that deals with the mole, okay? And it's a way of counting by weighing, which is what your experiment will be. I think it's experiment number 8, okay? If you have so many individual pieces and it'll take you forever to count them, there is an easier way to count them by just weighing them, as long as all those individual pieces have more or less the same mass, okay? If each one of these bolts weigh about 0.5 grams, and I have somewhere in the order of about 30 bolts, okay, or nuts, I mean, then that whole thing would weigh about 15 grams. So if I had 15 grams of bolts, I know that I've got 30 of those, not bolts, I mean nuts. If I weigh 15 grams of those nuts and each one weighs 0.5 grams, then I know I have 30. That's counting by weighing. And you do that in your grocery store, okay? You kind of do that in your grocery store. So let's take a look at this right here. Counting by weighing. And why do we do that? This is actually, the reason why we do that is because it's the most convenient way of counting atoms, because atoms are so small, okay? 12 grams of carbon atom actually contains 6.02 times 10 to the 23rd carbon atoms, okay? If I have a scale and I put water molecule and I put 6.02 times 10 to the 23rd water molecules on that scale, guess how much that would weigh? It would weigh 18 grams. So we have something called the molar mass. The molar mass tells you the individual mass of the atom, like water. 2 hydrogens, 1 oxygen. Hydrogen is 1 AMU a piece times 2. Oxygen is 16 AMU times 1. That's 18. So 1 water molecule has a mass of 18 atomic mass units. If you put 6.02 times 10 to the 23rd on a scale, that 18 atomic mass unit would translate to 18 grams, okay? Carbon has a mass, a carbon-12 atom has a mass of 12 atomic mass unit. If you put 6.02 times 10 to the 23rd carbon atoms on a scale, it would weigh 12 grams. So you see how we can convert the atomic scale, AMU, to our scale, grams, if we use this 6.02 times 10 to the 23rd value. That is a conversion factor. It takes the atomic scale and magnifies it up to the macroscopic scale, gram scale that we are used to. That's why we use the mole, because 6.02 times 10 to the 23rd is also called Avogadro's number. Some people call it avocado's number, but it's Avogadro, a scientist, and that represents 6.02 times 10 to the 23rd anything. You could have, and that's 1 mole. You could have a mole of sand. You can have a mole of pennies. You can have a mole of carbon atoms. You can have a mole of methane molecules. You can have a mole of hydrogen molecules. You can have a mole of hydrogen atoms, okay? So it's a way of magnifying the atomic scale to our scale, and that's why it's so important, okay? That's why it's so important. So the first thing I want to do is show you this right here, because again, it takes the atomic scale and brings it up to the gram scale. And NAV is 6.02 times 10 to the 23rd. That's 1 mole. And then we use the atomic weight. Water, it would be 18. Carbon atom would be 12. Oxygen molecule would be 32, 16 times plus 16, okay, to make that conversion. Because if you got oxygen, the molecule, and you have 32 grams of it, then that represents 1 mole. So we say that the atomic weight of a chemical, that many moles of that particular chemical based on its atomic weight weighs that many grams. 1 mole of water weighs 18 grams. 1 mole of carbon atoms weigh 12 grams. 1 mole of oxygen atoms weigh 32 grams. So we say for oxygen, the molar mass is 32.0 grams per 1 mole. We can say that 32 grams equals 1 mole for the oxygen molecule. For the oxygen molecule, for the oxygen atoms, it would be 16 grams equals 1 mole. There's a difference. Oxygen atom is O, oxygen molecule is O2. There's twice as many oxygen in oxygen molecule. So that's what you guys are going to be using when you use the mole. You're going to use this concept, Avogadro's number and the atomic weight of the chemical. And you know how to calculate the atomic weight of a chemical if you just look at the periodic table and look at the mass of the elements that make up that chemical and add them all up. For example, sugar. Sugar is C6H12O6. Carbon has a mass of about 12.0. Hydrogen has a mass of about 1.0. Oxygen has a mass of 15.99. We'll make it 16.0. So to get the atomic weight of this chemical right here, okay, let me like this. So it's C6H12O6. So we got 6 carbons, and the 6 carbons 12.0. So 6 times 12 equals 72. We've got 12 hydrogens, and each hydrogen weighs 1.0. So 12 times 1 is 12. And you've got 6 oxygen, and each oxygen is 16. So 16 times 6, 96. So when you add this all up, 180 grams of glucose represents 1 mole. 180 grams of C6H12O6 equals 1 mole equals 6.02 times 10 to the 23rd glucose molecules. Okay, that's how you figure out the atomic weight or the molar mass of a chemical. You sum the mass of the individual atoms that make up that chemical. Okay, so now that you know that, let's move on and let's do this. Okay, I've already stressed that. But what I want to do is, the reason why chemistry can be frustrating is because there's so many definitions of moles. Okay, mole is not only 6.02 times 10 to the 23rd, but it also is a conversion factor. It's also a way of taking the atomic scale and making the macroscopic scale. These are the many definitions of a mole. And depending on which one you use, depends on the problem that you guys are solving, okay? 6.02 times 10 to the 23rd anything. A magnifier between atomic scale and macroscopic scale, a conversion factor, a chemistry dozen, the sum of the atomic mass of all the elements in a substance when the mass is expressed in grams. That's what we did right here when we took C6H12O6 and we said that 180 grams equals 1 mole. That's that definition right there, okay? It's also the ratio of elements in a substance as indicated by its chemical formula. This 7 tells you you have 7 moles of carbon. This 3 tells you you have 3 moles of nitrogen. It can also mean that you have 3 nitrogen atoms. But if you have 1 mole of this guy, if you have 1 mole of that guy, then you have 7 moles of carbon, 5 moles of hydrogen, 3 moles of nitrogen, and 6 moles of oxygen if you have 1 mole of that guy. Okay, so just want to make sure that. So that's what that means in terms of that. And then finally, the last definition is this right here. It's the ratio of the elements combined in a chemical formula as indicated by the balance equation. These guys right here also represent moles. And you'll see that once we start doing stoichiometry. Okay, you'll see that once we start doing stoichiometry. Okay, so we're going to concentrate on this for now, and maybe this. And then after spring break, we'll look at that. So let's take a look at this. And this is what I mean by dimensional analysis. You want to use dimensional analysis. How much will 5 times 10 to the 26 molecules of water weigh? Okay, so you've got water, and you've got that many water molecules in here. And the question is, when you put it on a scale, what does the scale read? We need to do dimensional analysis for that. The first thing that you need to remember is you need to remember Avogadro's number, 6.02 times 10 to the 23rd molecules equals 1 mole. You need to remember that. Then you're dealing with water. What is the atomic molar mass of water? Water has 2 hydrogens and 1 oxygen. That's 18.0 grams equals 1 mole. These are the 2 conversion factors that I need to solve this problem. Okay, so how do I start? The way I start is I use this number first. Okay, this is the information I need, the molar mass and Avogadro's number. To start, I'm going to use 5 times 10 to the 26 molecules. So I'm going to put 5 times 10 to the 26 molecules as my starting point, right there. Then I look at the units of that. That has molecules in it. Look at Avogadro's number. That has molecules. And on top is my other unit, mole. Okay. Right now, I'm just letting the units walk me through. This has mole. It has to cancel with the next conversion factor. So that has to be mole down here. I try and color code this. Look up here. You have moles and grams. Grams have to go on top. Whatever unit you haven't used has to go on top. And that's what the question is. How much does a water molecule weigh? So your answer is going to be in grams. The next thing you want to do is just write the numbers. Avogadro's number is 6.02 times 10 to the 23rd, 1 mole. Okay, and then molar mass, 18.0, 1 mole. And then all you have to do is the math. Take 5 times 10 to the 26 molecules divided by 6.02 times 10 to the 23rd, multiplied by 18, and you have your numbers. Okay. If you do this via dimensional analysis, what happens is that you get the right answer. You get the answer that you need. And here, let me show you how that works out. See how I let the units walk through this? That's Avogadro's number. That's this guy right here. And then the mole, I let the units walk me through. Has to be in the denominator so it can cancel. And then I use 18 grams. And so all I got to do in my calculator now is take 5 times 10 to the 26 divided by 6.02 times 10 to the 23rd multiplied by 18. And I get that value, 14,950 grams. That's why you need to learn dimensional analysis. You're going to do that a lot in chapter 7. Okay. I don't know why I got I think an allergic reaction. My face is itching. Anyway, let's take a look at the next question. What is the volume of this water in liters? What you need to do is worry about the density, because the mass and the volume is related by the density of the material, okay? The mass and the volume is related to the density of that material. So we start with 15,000 grams. And then I want to use this, grams on the bottom, milliliters on top. So use this unit and that unit, and then milliliters on the bottom, liters on top. And then I just write the numbers with the unit. I have 1,000 with the milliliters, 1 with the liters. I have 1 with the grams, 1 with the milliliters, and then I just calculate my answer. So that's what you will see. Again, I cannot emphasize using dimensional analysis. I guess I didn't use 15,000. I used this number here. Still the same idea. Okay. Comes out to about 15 liters. Comes out to 15 liters. Let's see how this is done in a stoichiometry problem. Okay. The way you want to work these problems is through this chart. Okay. This chart shows you the steps in doing dimensional analysis. Okay, this chart shows you the steps in doing dimensional analysis. If you have a compound, look down here. If you have an atom, look down here. Then if the problem gives you the mass, you start with B. If the problem asks you to calculate the moles, then you go from here to here, you go from B to D, but you need the molar mass as the conversion factor. That's your conversion factor in this particular case, okay? I see that there's a couple things in the chat, but I don't see anything in the chat over here. Let me just double check. Okay. Okay, you guys are probably texting or chatting amongst yourself, so that's fine. Okay, yeah, you could do that for those of you who want to use the text. If you don't, if you need, we can do this later. Okay, Kim, talk to me after class. I can help you out with that. So again, going back to this, what I want you to see is how to use this chart to make stoichiometry super easy. Right now it's complicated because it's like trying to understand what's going on, but it can be made super easy if you learn how to use this chart. If you have like the mass of water and you want to know the number of molecules of water, then you start with this right here. You start at B because that's the mass of a compound. And then you end up at D because that's the moles of that compound, but you would need the conversion factor, the molar mass. Okay, you would need the molar mass. So the way you do that is, let's say that I have 50 grams of water, and I want to know how many molecules that is. According to this chart, I would need to go from B to D because that's what I want, the moles of that compound. Okay, and in order to get that information, I need Avogadro's number. I need the molar mass of water, 18.0 grams per mole. Where did I get that? I got that. These are stepping stones, molar mass. Okay, so how would I set that? I would set that up by 50 grams of water. The molar mass of water is 18 grams per mole. So I would put grams here, moles here, and then I would get my answer. See how I'm using the molar mass to make that calculation? 18 would go with the grams, 1 would go right here, and I would just take 50 and divide it by 18, and I would get the moles. of water. Again, you're using this scheme right here. If I wanted to go from mass to molecules, how many individual molecules of water I have, then first thing I would do is calculate the moles of water, and then I would use Avogadro's number. That's this number right here to make that last step. And I know that for every 1 mole of whatever, I have 6.02 times 10 to the 23rd. That's Avogadro's number right there. And then that would be my conversion factor in that second step. So the way you read this particular chart is the following. You first need to look at the question and understand whether or not you have a compound or an atom, compound or an atom. Then you have to decide, in my given information, do I have the mass of that compound, the moles of that compound, or the molecules of that compound? That's where you start. And then what you would do next is find what you are looking for. What is the question? So you can figure out what steps you need to get there, because it's all based on dimensional analysis. It's all based on dimensional analysis. So let's take a look at this question. This right here is more complicated, of course, but this is what you guys are going to learn once you start doing stoichiometry. This right here is the balance equation. That's why you need a balance equation. Okay. But let me do an example so that you can see how easy this is. Let's take a look at this. What is the number of molecules of 2.9 moles of TNT? So that's the question. You have 2.9 moles of TNT. TNT is trinitral-toluene. It's the main ingredient in dynamite. And I want to know the number of molecules of 2.9 moles of TNT. And then the second question is, how much will this weigh? And the third part is, how many nitrogen atoms are in 1 gram of TNT? It looks pretty daunting, but it's super easy. Okay, it's super easy. And here's what I'm going to show you. Okay, we're gonna look at this chart. This is the first question right here. What is the number of molecules in 2.9 moles of TNT? So this is the information we have. First question you might ask is, TNT an atom or a molecule or a compound? Okay, hopefully you guys said it's a compound. Okay, trinitral-toluene is a compound. So we're going to start in this column right here. That's the first thing that you need to do. You need to figure out whether it's an atom or a compound. TNT is a compound. Okay. What information do we have? We have 2.9 moles. So do we have B, D, or C? Hopefully you guys said D, okay? Hopefully you guys said D. We have moles of TNT. So that's where we're going to start. We're going to start with D. And the question is, what is the number of molecules? Where are we going? Are we going to mass or are we going to molecules? You guys know that you're going to molecules because that's what the question is asking. So we're going from D to C. So that's our path, D to C, and we have our answer. Okay, D to C. So that's how you read this thing. You just have to figure out what information is the question giving you. I'm really getting another allergic reaction. I don't know why. Anyway, D to C is the path. Now let's set it up. You start with the information that's given. So I'm going to put 2.9 here, 2.9 moles. And according to this chart, I need Avogadro's number. I need Avogadro's number. Okay, in order to go from D to D. So what is Avogadro's number? 6.02 times 10 to the 23rd anything, in this case molecules, equals 1 mole. So I have moles here, I need moles down here, and molecules up here. I abbreviate molecules, by the way, MOLC. Now, what numbers do I put here? Well, 1 here and 6.02 times 10 to the 23rd here. And then I just carry out my math. It would be 2.9 times 6.02 times 10 to the 23rd, and that would be my answer. And you can see that Let me clear this up for you. Oops. I guess I don't solve it. I do this whole thing. Let's do the second one. I just want to show you the path first, and then we'll put it, we'll solve it. How much will this amount weigh? So we're going to go from D, this amount is going to weigh to B. So that's the path for the second step, D to B, okay? And then finally, how many nitrogen atoms are in 1 gram of TNT? So TNT is a compound. That's this right here. But the question is asking atoms. That's this right here. Okay. And it wants to know how many nitrogen atoms. That's this right here. Atoms of element. So somehow we're going to have to go in this particular step, D to Y, Y to X. Those are the path I need with these conversion factors to solve that problem. Now, let me tell you a little trick about formulas. You see how TNT is C7H5N3O6? The formula is the conversion factor. The formula is the conversion factor. If I have 1 mole of this guy, then that is equal to 3 moles of nitrogen. Okay, that is equal to 6 moles of oxygen. That is equal to 7 moles of carbon. That's because if I have, if I have 10 C7H5N3O6, if I have 10 of those, then I have 7 times 10 carbon. I have 3 times 10 nitrogen. Okay, if I have 1 mole of C7H5N3O6 TNT, then I have 3 moles of nitrogen. So the formula is the conversion factor, and that's where you use that. That's where you use that. So this path, this last path, is D to Y to X, and then you have your answer. Okay, D, that's this step, to Y to X, and then you have your answer. So let's see how that plays out. Okay, let's see how that works out. Oh, I have 1 gram. I'm sorry, I have 1 gram, so I actually have to start over here. I forgot about that. Okay, so it's B to D. Let me clear this up for you. Okay, it's 1 gram is that. Nitrogen, many nitrogen atoms is that. So it's B to D, D to Y, oops, Y to, I think that basically is Y to X, Y to X. That's our path, okay? So let's take a look at this first step. Remember I told you that the path is D to C. So we have 2.9. We're going to put 2.9 right there. And then we're going to use Avogadro's number. And that's basically what you will see right here. 2.9 moles, 1 mole of TNT, 6.02 times 10 to the 23rd. That's Avogadro's number. And then we have our answer. You just do the math. Okay, you just do the math. Let's take a look at this one right here. We have 2.9 moles of TNT, and we're trying to calculate the mass of TNT. So we start with 2.9 moles of TNT, and then remember we're using the molar mass, and the molar mass is 227 grams of TNT per 1 mole. 1 mole, 227 grams. You just do the math. You just do the math. The last one is 1 gram of TNT. So we're going to start out with 1 gram here. We're going to go from B to D. That's going to use the molar mass of TNT. That's that. D to Y, we're going to say that for every 1 mole of TNT, there are 3 moles of nitrogen. That's the conversion factor where you use the formula right there. And then finally, we're going to use Avogadro's number. We're going to put moles of nitrogen down there and 6.02 times 10 to the 23rd on top. And then we just do the math. So this chart that I'm showing you allows you to do stoichiometry without thinking really about the problem. All you have to do is set it up and then use the conversion factor to figure out what the answer is. It's the best way to do stoichiometry. It's the best way to do stoichiometry. It's via dimensional analysis. That's why I told you back in chapter 2, invest time in learning dimensional analysis. It will save you a lot of time in stoichiometry. It'll save you a lot of time. But I'm going to spend about 15 more minutes just talking about the lab that is scheduled over spring break, but it's not due until the Sunday after spring break. Okay, it's not due it's due the Sunday after spring break. This Sunday, you're doing molecular geometry, but the Sunday after spring break, not Easter Sunday, but the Sunday after spring break, this is due. But it's good to get a head start because your midterm is coming up. So let me change screen here to show you that. So this is your activity, okay? This activity right here simply says balance the equation. Sodium chloride plus silver nitrate. This right here is a double displacement reaction. So the sodium will bump off silver and you get sodium nitrate, and the silver will bump off sodium and you get silver chloride. So it's a double displacement. The cation of one is going to replace the cation of the other. Likewise here, the sodium is going to substitute for the hydrogen is going to substitute for the sodium. Okay, that's why this is blank, because in a double displacement reaction, it's pretty much known what the answers will be. Okay, here it tells you what the product is. I give you the name. So zinc plus chlorine gives you zinc chloride. You guys should know that zinc is always +2, chlorine is always -1. So the formula for zinc chloride is ZnCl2. Once you write the formula, then you can balance the equation. You got to get the formula right first. If you don't get the formula right, no use balancing the equation. Let's take a look at this one right here. Number 3, iron 3 sulfide. That's what this chemical is. Iron 3 sulfide. It's a +3 iron, Fe2S3, plus hydrogen cyanide. Forms iron 3 cyanide. That means the iron is a +3. You guys should know cyanide is -1. So crisscross, you need 3 cyanides for every 1 iron. That's the formula. And then dihydrogen monoxide, monosulfide, H2S. Once you get the formula, then you can balance the equation. That's why I give you the name. It's to refresh, to make sure that you guys remember atomic nomenclature, naming these things. Okay. Cobalt 3 carbonate. Cobalt's +3. Carbonate is a polyatomic ion. It's -2. Crisscross, you need 2 cobalt and 3 carbonates for that formula to be correct. Okay, so that's what this part of the activity is. You just are going to write the formula based on what you guys learned in chapter 6. Once you have the correct formula, then you need to balance it. Remember, if you have a polyatomic ion like a carbonate, balance it as a unit, balance it as a whole. Don't break it up to carbon and oxygen. It's going to drive you crazy. This right here is the name, sulfur dioxide, SO2, oxygen. Again, it's not oxygen the atom, it's oxygen the molecule, O2. We're not going to tell you O2 when we say the reaction. We're just going to say oxygen, and it's up to you to know it's O2. It's the way it's found in nature. So that's O2, and sulfur trioxide is just SO3. Ammonium nitrate, ammonium's NH4, nitrate's NO3. NH4 +1, nitrate is NO3 minus, so it's a 1-to-1 ratio. Forms nitrogen, again, N2, oxygen, O2, and water. You guys know water, okay? Sodium bicarbonate, that's baking soda. Baking soda's NaHCO3, sodium bicarbonate. The bicarbonate ion is HCO3, okay? Acetic acid. Acetic acid is the main acid in vinegar. It's H, telling you it's an acid, and then the acetate ion is C2H3O2. It's a -1. And so you get sodium acetate, carbon dioxide, and water. So you just have to write the formula. A lot of times the ratio will be 1 to 1 to 1 to 1. So you don't even need to balance it. It's already balanced. But you got to double check. You got to double check. Okay. So the rest of these are just balancing equation. Here, look up tungsten, atomic symbol W. Yttrium, that's not Y. Okay. You need to look that up yourself. Sulfur hexafluoride. Okay, that's just sulfur and 6 fluorines. So calculate the molar mass of all those things. Tungsten oxalate, that's tungsten 5, and oxalate is C2O4 oxalate. It comes from oxalic acid, okay? And the charge of the oxalate ion is -2. And then you have 4 waters on that. Look at experiment number 4. Remember, it was cobalt chloride hexahydrate. It's COCl2 6H2O. Well, this has 4H2O in the formula. When you calculate the molar mass, you need to include the water as well. So this exercise right here is just for you guys to calculate the molar mass of all these chemicals, either the atomic weight or the molar mass. This right here, how many atoms are in 11 molecules of sulfur hexafluoride? Let me give you a similar example, okay? Because a lot of people will look at this, and because you don't understand the definition of a molecule, or at least it's hazy, it's gonna drive you crazy, okay? But it's really not that hard. It's really not that hard. Let's take water, okay? Water, H2O. How many atoms are in water? You would say 3, 2 hydrogens and 1 oxygen, okay? So for 1 molecule of water, you would have 3 atoms. How about if I have 2 molecules of water? Well, if I have 2 molecules of water, that would be H2O, that's 3 times 2, that's 6. That's what this question is. 11 molecules of sulfur hexafluoride. First, get the formula of sulfur hexafluoride. How many atoms total in 1? How many would there be in 11? It's not hard if you understand the problem, okay? It's not that hard. So don't make it harder. A lot of times you guys will make it harder than it is. This one's simply asking, if you've got 11 of these sulfur hexafluoride, how many total atoms? This one right here, how many moles of water are in 5 moles of tungsten 5 oxalate tetrahydrate? Well, 1 tungsten 5 tetrahydrate has 4 waters, one of them, okay? So if you've got 1 mole of that guy, then you would have 4 times Avogadro's number. You can use dimensional analysis, and the conversion factor is for every 1 mole of tungsten 5 oxalate tetrahydrate, for every 1 mole of that, you got 4 moles of water. That's your conversion factor. So if you got 5 moles of that, how many moles of water do you have? Again, the best approach is dimensional analysis. You have to find the conversion factor, okay? The next question, and I think I will leave it at that because this next set deals with balancing equations and stoichiometry, but I'm just going to go through this first page, and then I'll come back after spring break, after you guys have digested all of this, and you have time, okay? So send me questions if it doesn't make sense, and I can walk you through the dimensional analysis, or watch this video again. This one right here, what is the molar mass of a molecule that weighs 2.99 times 10 to the minus 23 grams? What is the identity of that molecule? Let me help you with that one, because that one's a little bit challenging. Okay. What is the molar mass of a molecule? And remember, molar mass is grams per mole. Okay, that weighs, the mass is 2.99 times 10 to the minus 23 grams. Okay, and what is the identity? So from the molar mass, I should be able to ID the element. So the first thing that you will, again, your best approach here is dimensional analysis. If you take a look at the, you have one molecule equals 2.99 times 10 to the minus 23 grams, okay? If you remember molar mass, the molar mass is grams per mole, okay? That's the units of molar mass. Water is 18 grams per mole. So what you need to do is look right here. You've got grams on top, 2.99 times 10 to the minus 23 grams, okay? And that's per one molecule. You need to figure out how to convert molecule to moles, because you already have grams on here. Dimensional analysis. So what conversion factor can you use in order to relate molecules to mole? I'll wait for your response. What is a conversion factor that relates moles to molecules? Anybody? Are you still there?
Yes.
What we've talked about it numerous times in the previous.
D to C, the net.
Yeah, but what is that number? What do we call that?
6.02 times
6.02 times 10 to the Avogadro's number. Exactly. Exactly. It's 6.02. 6.02 times 10 to the 23rd molecules equals 1 mole. You see how you make this problem easier if you do dimensional analysis? You see how you have molecules here? You need molecules up here. And you need moles down here. Now you put 6.02 times 10 to the 23rd with the molecules and 1 moles on top. And then if you put it in your calculator, 2.99 times 10 to the minus 23rd times 6.02 times 10 to the 23rd. And you will get a number that looks like, let me see. Now, before you all leave, punch this into your calculator and verify your answer, because what I have found out is that 7 out of 10 of you don't know how to use your exponent key in your calculator. Okay, and if you don't know how to use the exponent key in your calculator, you may know how to solve the problem, but you're punching it all wrong in your calculator. You guys should get 17.99 or 18.0 grams per mole. If you're not getting that, then I need to show you how to use your calculator, okay? If you're not getting that, then you have something wrong. You're not using your calculator correctly. And that's a tough part, and we need to get you straightened out on that. Take 2.99.
Quarters at 25, right?
Yes.
Okay, 2.99 times 10 to the minus 23 times 6.02 times 10 to the 23, positive 23. And you guys should get about 18.0 grams per mole.
Yeah, I got that.
Okay. What's 18 grams per mole? What chemical weighs 18 grams per mole? You guys should know that.
Water.
Yep, water. See, these problems are not hard. They're not. but it allows you to practice dimensional analysis. Because if you can master dimensional analysis, then you've got stoichiometry pretty much mastered. That's the best way to approach stoichiometry. Otherwise, you're going to go crazy because there's so many ways to solve a stoichiometry problem. But if you know what you have, what you're solving for, and then the steps, the conversion factors to get there, it'll be a cinch. These steps right here that I have, I'm trying to illustrate to you that you don't have to figure it all out and get lost. All you have to do is read the stoichiometry map. And if you know what you have and where you're going, then you know the conversion factors to use to solve that problem. And that's basically what stoichiometry is about.